welcome to lecture series. Already we have introduced the concept of invariant subspace in my last lecture with couple of examples and the characteristic of the invariant subspace also we have seen it. We will continue that because our destination is to understand the linear operator in a more simplified form. So, for this let me introduce another terminology. So, before that let me consider, let T be a linear operator on a finite dimensional vector space say V over the field capital F. Let W be a subspace of V. Let alpha belongs to V be any element. Let ST W alpha denote the set of all polynomials P such that Pt operating on alpha belongs to W. So, this implies that ST W alpha is collection of all polynomials over the field F such that for any F belongs to ST W alpha, F of t operating on alpha will belongs to W. Certainly ST W alpha is non-empty. How can I say it is non-empty? See, if the dimension of the V is finite, then definitely a finite degree polynomials over the field F will be there which will annihilate the operator T. So, if it annihilates the operator T, I mean F of T equal to 0 operator, then certainly F of T operating on alpha will be in the W, because W is a subspace of vector space B. So, characteristic polynomials, minimal polynomial all will be there in the ST W alpha. So, since characteristic polynomial and minimal polynomial are there in ST W alpha. So, it is non-empty. It is not only non-empty subset of the vector space of all polynomial function fx. So, I can say that ST W alpha will be subset of fx, that is vector space of all polynomial functions defined over the field F, because that is also field. So, I can say this will be also subset of this one please. Okay. We will prove shortly that this is also a subspace of the vector space f of x also. Claim ST W alpha is a subspace of vector space, here this one please. I consider the operator is T defined over the vector space V, which is defined over the field capital F please. Now, with respect to that field, we have defined another vector space, or you can say field of all polynomial function, that is f of x, this one. This is also a vector space. So, this subset STW alpha, what we have what I have already constructed here for a given w and alpha, we see that this is a subset of f of x. And now, I want to prove that it is not only subset, it is also a subspace of f x also, subspace also. Let me consider in the very beginning here W be an invariant subspace please, invariant subspace under T. Now, STW alpha is a subspace of a vector space, I have to prove it please. How? Let f and g belongs to STW alpha. So, this implies f of t alpha will basically belongs to W, and g t of alpha also belongs to W. So, for C belongs to capital F, C times f plus g of t, which is equal to C f of t plus g of t, and we see that this when operating on alpha, this will be like this, this is equal to C of f of t alpha plus g of t of alpha. Now, this each of them will belongs to, this belongs to W and this also belongs to W, because f and g both belongs to STW, and its f of t operating on alpha will be inside the W. This implies that CF plus G, CF plus G also belongs to your STW alpha. So, this implies the set STW alpha is a subspace, of the vector space f x. I am not talking that it is subspace of the vector space V, it is a subspace of vector space f x please. Another interesting is that if W is invariant under T, then W is also invariant under T square, because T square of the W is equal to T of T W, but T of W is subset of W. So, this implies this will be T square of W will belongs to W. Okay. So, this implies if W is invariant under T, it is also invariant under T square, and it is also invariant under any integer power of positive integer power of T also. So, this implies W is invariant under any t to the power k also. I mean t into t into t up to k times please, that is t to the power k please. So, this implies if W is invariant under T, then W is also invariant under f of t, where f is a polynomial over the field capital F. So, you see that if W is invariant under T, then it will remain invariant under any operator f t, where f is basically polynomial over the field capital F, when the W is a vector space, subspace of a vector space V defined over the field capital F please. So, we see that the way we have constructed a set of polynomials S t W alpha, we see that this is subspace of the polynomial space, I mean vector space of polynomial functions f of x. In fact, I will say that this S t W alpha is an ideal of the polynomial field f x please. This is a field, I am saying field, it is also a vector space. So, S t W alpha is an ideal of f x. I mean both in the case of, see, W is invariant. So, I will not consider left ideal or right ideal. The ideal generally we used to say when left ideal equal to right ideal, then I will say that it is a simply ideal please. I do not want to confuse it. So, simply I will say that is a subset of the field f x will be an ideal if it is basically satisfy the definition of the group with respect to one operations, that is vector additions, and of course, it satisfied closure property with respect to multiplications, and it satisfied that if I consider f belongs to S t W and g belongs to the f x, then g into f must belongs to S t W, then only I can say S t W alpha will be an ideal. Okay. So, let me prove this one. Let f belongs to S t W alpha and g belongs to any polynomials in f x please. So, f of t alpha will belongs to W, f t alpha will be W. We know if f t alpha belongs to W, then for any g belongs to f x, g t operating on f t alpha will also belongs to W, already you have proved it. If W is invariant under T, it will be invariant under any polynomial in T. So, since this is a element in W, so g t of that element must be inside of W, g t of that element will not be please. So, this implies g into f belongs to also S t W alpha. So, what I have found? We have seen that if a function, polynomial function f belongs to the your S t W alpha, any other polynomial g belongs to the f x, g into f also belongs to STW alpha. Here I have multiplied from the left. Now, note that FTGT equal to GT FT. So, therefore, left multiplying from left or right is a irrelevant place. So, I can say that STW alpha is an ideal of Fx. Okay. Since it is an ideal, definitely there is a generator for this, I mean to say least degree monic polynomial. So, there exists a least degree monic polynomial, say G belongs to STW alpha, such that all other elements of STW alpha is multiple of G. This least degree monic polynomial is called as T conductor of alpha into W. So, T conductor of alpha into W is the least degree monic polynomials, which is basically generator for the ideal STW alpha place. So, this implies if W is equal to 0 subspace, then for any alpha belongs to V, the STW alpha will be the set of all polynomials which annihilate alpha T. I mean to say, for F belongs to STW alpha, your FT alpha equal to 0. If I consider W is a 0 subspace of the vector space. So, one simple case when W is a 0 subspace, then for any element alpha belongs to V, the ST alpha, I mean the T conductor of alpha is basically T annihilator of the alpha place. So, T conductor of alpha is here as T annihilator of alpha place. Now, the question is this, when W equal to 0 subspace, then the characteristic polynomial will be there or not, because characteristic polynomial annihilate alpha. So, characteristic polynomial will be in this set also. What about the minimal polynomial? Minimal polynomial also will be in this set also. Now, let me take extreme case. If W is equal to the entire V, then we know V is also invariant under T. So, in this case, what about the ST V alpha? Then ST V alpha will be what? Here the polynomial will be, I mean it will be much bigger set. This STV alpha will be much more bigger set place. So, if I consider the least degree monic generator of this one, definitely this will be much smaller compared to the least degree monic generator of the ST W equal to 0 subspace place of alpha place. I mean these are two extreme, this is a 2 and other one is say 1. So, both of them are ideals, but the monic generator of the second one will be certainly include your monic generator of first one, but reverse is not true. So, the monic generator of second one must divide the monic generator of the first ones. This implies for an invariant subspace, W of V under T, the T conductor of ST W alpha, ST W alpha must divides the minimal polynomial of the operator T, because minimal polynomial will be by default in each of the set place. So, based on this concept we can write one nice results which I will use to simplify the operators. So, before applying that concept, let me define one terminology, it is called triangulable operator. Triangulable operator. Let T be a linear operator on a finite dimensional vector space capital V over the field capital F. T is said to be triangulable. T is said to be triangulable provided there exists an order basis for vector space V such that the matrix representation of T with respect to that order basis is a triangular matrix. Triangular matrix. I mean to say that is, if V is of dimension n, then the matrix representation of T with respect to their order basis will be of the form of say like A11, A12, A1n, 0, A22, A2n, and it will be ANN is 0 and like this. So, the structure of this matrix representation of the T with respect to order basis B will be something like this triangular matrix space. Then only I will say that the given operator is triangulable. I will see under what conditions a linear operator defined over a finite dimensional vector space is triangulable. So, to understand that concept, let me introduce a small results in terms of lemma. It is like this. Let T be a linear operator on a finite dimensional vector space V over the field capital F. Let the minimal polynomial of T be of the form P equal to x minus C1 power R1 into x minus C2 power R2 and x minus Ck power Rk, like this. Let W be a proper subspace, of V. Then there exists alpha belongs to V such that alpha does not belongs to W and T minus C I operating on alpha belongs to W for some characteristic value C of T, please. So, it is given me that W be a proper subspace and it is also given that the minimal polynomial is product of linear factors. So, in this case the result says that for any alpha which is belongs to V but not belongs to the W, there exists a characteristic value C of T such that T minus C I operating on alpha belongs to W. So, according to given condition, basically we have to show that the T conductor of alpha, the T conductor of alpha is a linear polynomial. So, let beta belongs to V such that beta does not belongs to W. Now, the T conductor of beta, the T conductor beta will be of the form of say G is equal to x minus C1 power say E1 into x minus C2 power say E2 and x minus Ck power Ek. Why it is like this? We know that the T conductor of beta must divide the minimal polynomial and minimal polynomial having structure like this. So, the structure of G has to be like this such that G divides P. That is why the structure of the T conductor of beta will be like this. G T beta belongs to W. It is given to us, please. I mean, we have assumed, please. Now, since G is like this structures, what can you say about the E1, E2, Ek? Certainly, E1 cannot cross R1, E2 cannot cross R2 and Ek cannot cross Rk. That is true because G divides P. Is it possible that all Ei will be equal to 0? If all Ei I equal to 1 to k are 0, then I will have beta will belongs to W, which is not possible according to our hypothesis, which is not possible. So, at least some Ej not equal to 0. So, let G equal to x minus Cj. Cj is basically the characteristic value, please, x minus Cj into some Hx. I can write like this thing, please, such that Gt of beta belongs to W. So, this implies Gt beta, which is equal to T minus Cj I operating on Ht beta will belongs to W. I have taken Ej not equal to 0. So, Ej is basically more than 1. I mean, it will be like 2, 3, 4 like that. So, that is why I have written G is equal to x minus Cg as one of the factor and rest term. So, rest term Hx is a polynomial of degree less than the degree of the G, please. Now, Gt beta equal to this quantity. Ht beta does not belongs to W because degree of H is less than degree of G and G is the least degree monic generators. So, therefore, Ht beta cannot be in W, please. So, let Ht beta equal to alpha. So, we have Gt beta which is equal to T minus Cj I into alpha belongs to W, such that alpha does not belongs to W. So, we have proved that the T conductor of alpha is basically here as a linear polynomials x minus Cj, please. I shall use this concept to prove the nice result that is called triangulation of a linear operator, please. So, what we see here that if minimal polynomial of an operator is product of linear factors and the operator is defined over a finite dimensional vector space, then for any proper subspace W, for any element beta belongs to V not belongs to W, we see that the T conductor of beta will be basically a linear polynomial. I mean linear polynomial of the form of something x minus C, where C is basically a characteristic value of the operator T, please. I shall use this concept to prove the triangulation of a linear operator also. So, this will be done in the next class.